All right, let's talk about something you see literally every day, oscillation. That simple back and forth motion. We're going to unpack the really beautiful physics behind it, and we're going to do it by telling a story all about energy. So our story begins right here with this classic setup. You've got a block, a spring, and a surface with no friction. Now picture this. We pull the block to the side, we let it go, and whoosh, it starts sliding back and forth. It moves fastest right through the middle, then it slows down, stops for just a split second at the very end, and then zips right back the other way. And this is where things get interesting. This is our central mystery. Think about it. When the block stops, even for that tiny instant, its motion is zero. That means its energy of motion has to be zero too. But then a moment later, it's flying again. It's like the energy just vanishes and then reappears out of thin air. So where on earth does it go? Let's figure this out together. To crack this puzzle, we've got to meet the main characters in our story. And the first one up is the energy of motion itself. In the world of physics, we call this kinetic energy. You'll usually see it labeled with a K, and it's all about one thing: speed. The faster that block moves, the more kinetic energy it has. So where is the kinetic energy at its absolute maximum? Well, it's right as the block is blasting through the center point, what we call x equals 0, where it's hit its top speed. But kinetic energy is only half the story. It's got a partner in this dance, a totally different kind of energy that's just as important. Let's call it the energy in waiting. This is potential energy, or U. Now, this isn't energy of the block's motion. It's energy that's stored in the spring. A great way to think about it is like a drawn bowstring. When that spring is stretched or compressed as far as it can go, right at those endpoints where the block comes to a dead stop, that's when the potential energy is totally maxed out. It's just pure stored energy, ready and waiting to be unleashed. So here's the crucial point. We have these two types of energy working together. Kinetic energy belongs to the block's motion. Potential energy is all about the spring's position. And there are like two kids on a seesaw. They're perfect opposites. When one is all the way up at its maximum, the other is all the way down at 0. And that right there leads us straight to the solution to our puzzle. The energy never ever disappears. It just performs this brilliant, instantaneous costume change. This right here is the fundamental principle. The energy is in a constant dance, transforming from the energy of motion into stored potential energy, and then right back again. But, and this is the key, the total amount of energy, the sum of those two, which we call the mechanical energy, E, it never, ever changes. It remains completely, totally constant. And wow, these graphs show that dance just perfectly. Look at that. The green line is the potential energy, and the pink line is the kinetic energy. See how as one goes up, the other goes down? They're perfectly out of sync. But the real hero of this graph is that top black line, the one labeled E. It's totally flat. Their sum, the total mechanical energy, is always the same. Just a perfect, constant exchange of energy. And the math that describes this beautiful picture? Well, at its core, it's actually incredibly simple. The total energy, E, is just the kinetic energy at any moment in time plus the potential energy at that very same moment. That's it. Now, I know what you're thinking. When you plug in the specific, longer formulas for kinetic and potential energy in an oscillator, it suddenly looks, well, it looks a bit terrifying, right? You've got all these terms for the spring, the stretch, and these sine and cosine functions that have time in them. It really looks like the energy should be changing all the time, but there's a secret ingredient hiding in plain sight. And here it is. This little gem from trigonometry is the key that unlocks the whole thing. For any angle you can possibly imagine, sine squared of that angle plus cosine squared of that angle is always equal to 1. It's a fundamental truth of math. So because of that amazing little rule, all that complicated stuff with time, all the sines and cosines, they basically cancel each other out and become 1. And what are we left with? This beautifully simple result. The total energy E only depends on two things: K, how stiff the spring is, and XM, how far you pulled it back in the first place. That's it. It's a constant. The magic is revealed. So, okay, that's really elegant and kind of cool, but why does it matter? Well, because this idea of constant energy is an incredibly powerful tool. It lets us solve problems by just looking at a single snapshot in time, which is way easier than tracking the motion second by second. Let me show you what I mean. Okay, let's take a look at this problem.
We're told the total energy of a system is exactly 1 joule. We also know how far it stretches and how fast it goes at its peak. And just from those few pieces of information, we can figure out pretty much everything else about the system.
And the logic is actually pretty slick. To find the spring constant, K, we just need to look at the exact moment the block stops at its maximum stretch. At that instant, all 1 joule of energy is potential energy. So E equals 1/2 K times m squared, we can solve for K. Then, to find the mass, m, we look at the moment the block is flying through the center. There, all 1 joule is kinetic energy. So E equals 1/2 m times v squared. We can solve for m. And once we have K and m, finding the frequency is a piece of cake.
And when you run the numbers, boom, we find out the system oscillates back and forth 1.91 times every single second. And we figured that out just by knowing how the energy swaps from one form to another. That is the true power of understanding conservation of energy. So we've seen this perfect, beautiful dance where energy flawlessly trades places and the total amount stays exactly the same. But that leaves us with one last really important question. What happens in the real world? What happens when a force like friction gets involved and starts to steal just a tiny bit of that energy with every single back and forth swing? Well, that's a story for another time.